So I'm going to be talking about the research I did this past summer as a Claire Booth-Luce research scholar. So I'm going to talk a little bit about general relativity today and how that relates to astrophysical phenomena such as black holes, how I've been able to mathematically construct a two-dimensional black hole, and what all of this means for gravity. So to give a little bit of background, Albert Einstein came up with his theory of general relativity in 1915, and this theory revolutionized the way we look at gravity. So he was able to describe gravitational forces by combining the three spatial dimensions and time into a four-dimensional continuum called space-time. So the theory of general relativity describes how space-time curves in the presence of mass and how that curvature creates gravitational attraction. One problem with general relativity is that it doesn't really hold up in cases of extreme space-time curvature, though, like the ones that I study. So my research focuses on supermassive objects that are much more massive than our sun even. So my research focuses on black holes in particular, and black holes are some of these phenomena that cause extreme curvatures in space-time where general relativity breaks down. So a black hole, for those of you who are unaware, is a collection of mass that is so massive nothing can escape its gravitational attraction, not even light. So the radius where nothing can escape once it's been pulled in is called the event horizon of the black hole. So if no light can escape the event horizon, we can't receive any information from within the black hole. So how do we know what it's like past the event horizon? Well, since no light can escape, there are no observations or experiments we can do on Earth to know what it's like within a black hole. So we have to use math to try to describe it. So recently, Dr. Damien Eason from Arizona State University published a paper removing the singularity, the point at the center of the black hole where curvature is infinite and where general relativity really doesn't work. So he removed that singularity from a non-rotating, uncharged black hole, and I spent my summer here working with a couple of professors to try to reproduce his results. So the first step to removing the singularity is to simplify the equation that describes the black hole. So we start out with a four-dimensional equation, and then we integrate out two of the spatial dimensions. And since we have a spherically symmetric black hole, we can integrate out the angular dimensions without losing any important information from our equation. So we do that, and we're left with radius and time dimensions for a two-dimensional black hole. So the next step is to use, now that we have a simplified equation, we can use something called the limiting curvature hypothesis, which is really just a fancy way of saying we have to ensure that the curvature can only be so high in all of space-time. So we find a certain potential that ensures that all of space-time is bounded everywhere in space-time. And this means that the curvature within the black hole is no longer so high that general relativity can't describe it. And so we've effectively removed the singularity from the black hole equation now. So now that we've done this, we've done a lot of math, we have a new equation, but what does this mean for physics? So now that we no longer have a singularity within our equation, where we may in the future be able to see how matter actually interacts with each other in the black hole, which is something as of right now we have no way of knowing. So when we're able to examine these quantum interactions within the infinitely dense center of the black hole, this may reveal information that could be helpful to reconcile general relativity and quantum physics in the future, which is the essential problem in physics that, as of right now, has not been solved. By removing the singularity, we may also be able to, one day, prove or disprove theories such as wormholes and other theoretical phenomena that would be located at the singularity of the black hole. So for my MQP this year, I hope to explore some of these possibilities. I will also hopefully be removing the singularities from the equations for rotating and charged black holes as well. So thank you. I'll be here after if you have any questions.